I am really pleased to welcome all of you to the Department of Earth, Planetary, and Space Sciences public talk by one of our most distinguished faculty members, Professor Emerita Margaret Kivelson. I am Miguel Garcia Garibay. I'm Dean of Physical Sciences and Professor of Chemistry and Biochemistry. The Division of Physical Sciences encompasses 6 departments. Our host department today, Earth, Planetary, and Space Sciences, as well as Chemistry and Biochemistry, Physics and Astronomy, Atmospheric and Oceanic Sciences, Statistics, and Mathematics. Our faculty members are working on some of the big questions in science, and Professor Kivelson has spent her career investigating some of the big questions about space and other planets, especially Jupiter, the moons of Europa, and Ganymede, and their internal ocean and magnetic fields. The division is extremely proud that Professor Kivelson's achievements, which include recognition with the 2017 Gerard P. Kuiper Prize, which is, by the way, the highest award presented to planetary scientists. The prize is given to scientists, and this is the quotation, whose achievements have most advanced our understanding of the planetary system. This is certainly an accurate description of Professor Kivelson and a well-deserved honor. I would like to invite Professor Jean-Luc Margot, chair of the department, to the podium to share more about Professor Kivelson's career at UCLA. Jean-Luc.
Thank you. Thank you, Miguel, and good evening, everyone, and welcome to UCLA. I'm Jean-Luc Margot. I'm the current chair of the Department of Earth, Planetary, and Space Sciences, and I'm thrilled that so many of you joined us for an exciting event today. There will be a question and answer period after the talk, and so index cards are being passed around. So if you have any questions about the contents of the talk or careers in science, feel free to write down those questions, and we'll address them after the talk. Our speaker today, Professor Margaret Kivelson, is an incredibly accomplished scholar, mentor, and role model. She has published over 350 peer-reviewed publications that have been cited thousands, tens of thousands of times by other scientists. Because of the importance and impact of her scholarship, she has been elected as a member of the National Academy of Sciences. She has received many other awards, and the most recent one is the one Miguel just talked about, the Kuiper Prize of the American Astronomical Society, that recognizes outstanding contributions to planetary science. One of Professor Kivelson's most fascinating discoveries is that a moon of Jupiter, Europa, almost certainly has a global ocean underneath its icy crust. And that ocean may be 3 or 4 times as large as all of Earth's oceans, and it may be hospitable to certain life forms. So Europa has become probably one of the most important pieces of real estate in the solar system, thanks to discoveries from Professor Kivelson. NASA is planning a flagship mission to study Europa in greater detail. It will launch in 2022 and arrive in about 2025. So for the teenagers in the audience, your timing is perfect. By the time you get to grad school, the data will start pouring in, and you'll be poised for the next set of discoveries. We're particularly proud of having Professor Kivelson here at UCLA because she's been a role model and a mentor to many. She's mentored 15 or so graduate students to the PhD. She got her own PhD in 1957, and started at UCLA in 1967 when there were not that many women in science. So she's very much a pioneer, and she's been a source of inspiration to many who have followed in her footsteps. I'd like to recall an anecdote. When I was interviewing for a job here about 10 years ago, I very much wanted to meet Professor Kivelson, and I got to meet her, and I asked her, well, how was it to be a woman in science at UCLA? And her response, which was, I'm paraphrasing, but that she had found the environment to be a great environment for her development and with lots of supportive colleagues, That answer told me more about this institution than anything else that I heard during that 2-day interview. And it's probably one of the reasons I came here. So we're so proud of her accomplishments and role as a role model that we would like to establish a graduate student fellowship in her honor. This fellowship will be devoted to support the careers of outstanding graduate students with a preference, of course, for outstanding women in science. So if you wish to partner with us to enable this fellowship, please get in touch, and we'll probably have an announcement later about how to do that. Also, if you'd like to be informed about our future events, there's a tablet outside for which you can register for a mailing list. And for now, I'd like to welcome Professor Margaret Kivelson, and please join me in welcoming her to the podium.
All right, thank you very much, Dean and Chairman. It was overwhelming. Can everybody in the back hear me, or do I have to talk louder? You can't, okay. Or you can? Absolutely. Okay. I resist the temptation of dropping my voice at this point. My subject, as you see, is magnetic structures in the solar system, and I was inspired to choose this topic partly by a wonderful experience in seeing an eclipse of the sun in company of quite a few people who are here tonight and led by Jean-Luc. And this is multiple stages in the eclipse pasted together to make this great picture, which was probably taken not very far from where we were standing while we were watching the eclipse. So before I start, it's not only the dean and the chair I'd like to thank, but my colleagues in the department for inviting me to give this talk, and to the audience for coming, and to UCLA for having provided over decades an environment where I feel I've been able to thrive. Many of my colleagues are here tonight, and they have been those who've made it a great place to study and do research and work with students. And of course, the students themselves have challenged me and kept me interested in what I'm doing. And I've listed some of the special colleagues at the bottom, and many of these names were very much deeply involved in some of the work that I've done over the years. So think of them when I talk about some of the things that have interested me. Well, I'm going to start with the solar eclipse of August 21st of this past year. And I ask you, was it a big deal? My answer is, yes, it was. The New York Times tells us that 88% of American adults, about 215 million people, watched the solar eclipse either in person or electronically. So you're not alone, Miguel. And that's 30% more than participated in the presidential election. And we all voted for the sun. Almost 7 million eclipse glasses were sold through Amazon alone. And these folks are watching the partial eclipse and waiting for the moon to blot out the solar disk. And I ask, what did they see? Well, the sky above became dark enough to see Venus. Maybe other people saw more. I just saw Venus. The sun's disk disappeared, and when the bright light of the sun went out, our glasses came off, the temperature dropped noticeably, and the corona became visible. And a corona, of course, means crown, and it's the tenuous gases around the sun that are always there, but we don't see them because the sun is so bright that this pale light from the surrounding gases isn't visible until the moon blocks out the brightness of the sun. And an aside, isn't it amazing that the moon's distance and size are just right to blot out the sun? It never ceases to amaze me. So to the naked eye, it looked something like the image that I'm showing. You could see that there was some structure. You can see that there are regions above and below, right and left, that seem to extend farther from the sun. Well, the human eye is a remarkable organ and can see great contrasts, but a camera with a filter can do even better. And here is an image that was taken with, by superimposing two images taken seconds apart. Things don't change much even in a second. They were taken at different exposures so that the outer part was given more exposure so that you could see farther away from the disk than you do here. And now you can really begin to see the structure. A truly remarkable photograph is composed of 161 images taken by two cameras. This gentleman whose name appears here, Miloslav Druckmiller, is famous for taking eclipse pictures, but I think this one actually takes the cake. And you can see that there is a lot of structure. There are loops, there are things that come to peaks, and there are these lines that seem to emerge almost radially from the sun. And each of those is of great interest. But what you can see is that there is a great deal of structure in the emissions, in the light that we're seeing here. And it's the magnetic field of the sun that is imposing the order. And I'm going to tell you a little bit about how that happens. We can't see a magnetic field, but what we can see are the gases trapped by the magnetic field, and that's what we're seeing in this image. I think it's very interesting that one of our UCLA PhD students, he graduated 15, 20 years ago, has a group working with him. His name is John Linker. As a group working with him at a prediction activity. And what they did was to look at the magnetic field of the sun something more than a week ahead. This is the 14th, this is the 21st, and he predicted what the solar corona would look like, and I think you'll agree he did a pretty good job. Why did he do a pretty good job? Because the magnetic field of the sun governs all of this structure, and he had some advanced understanding of what that field would look like. One solar eclipse doesn't look like the next, and to eclipse experts, you can show a picture and they'll say, oh yeah, that's the one I saw in Libya in 2004, or oh yeah. So this is really a unique situation. So the question then is, what is the camera imaging? What is the prediction modeling? I've told you the magnetic field is playing a role. That's imposing the structure, the shapes. But what we're actually seeing is not the magnetic field, because the magnetic field isn't visible. So what is it that we're seeing? We're seeing the gases of the corona. And these are very special gases because the corona, remember that's this whole diffuse region from which we see light around the sun. The gases of the corona are electrically charged. The temperature of the corona is a couple of million degrees. So it's a very, very hot environment. And at those temperatures, even the most recalcitrant atoms give up their electrons. For our chemist in the audience, It was 13 times ionized iron that gave us the opportunity to figure out the temperature of the corona. So these gases are electrically charged, but they have no net charge. They just have electrons just enough to balance the positive charges of the ions. And there are as many negative as positive charges. And a charged particle is trapped by a magnetic field. Magnetic field changes the motion of a charged particle and doesn't let it go easily in directions across the field, but lets it flow very, very easily along the field. And that is why the plasma, the charged particle gas, maps out the magnetic field, because the particles are tied to the magnetic field, free to move up and down like beads on a string. So we're seeing sunlight scattering off the charged particles that are tied to the magnetic field. And the magnetic field is very complicated. And here I'm showing you a video, which, this is just a piece of the solar surface. It's being filmed in ultraviolet light. It's a video that takes about 10 hours, so it's sped up. You don't have to sit here for 10 hours to watch it. We're looking at a small portion of the solar surface, and that these loops are in constant motion and sort of spewing material out. I'm just going to move on and not worry about it, but I do hope the rest of the movies show. Okay, so the people can't resist giving names to things, so you don't have to pay any attention to it. This image shows you that we have names for each one of these different shapes, but basically, if you look at this is a different eclipse, not the one that from 2017, but what you see is arches, and you see these almost ribbons going radially out from the sun. Here's a nice one of the arches that you can see. And the sun is in constant, the solar surface is in constant motion. The gases are bubbling up. They're changing the magnetic field, even though the magnetic field is trying to hold on to them. And if they get hot enough and start moving fast enough, they can actually pull out the magnetic field with them. And what happens is that the sun is the source of an outflowing plasma that stretches the magnetic field beyond the disk into an almost radial structure and then proceeds to flow out through the whole solar system. And it turns out that the magnetic field of this plasma flowing out from the sun, which we call the solar wind, is critical in modifying the shape of the magnetic field in the vicinity of the planets, comets, any object in the solar system. And we can't see that, but it does impose structure. So I'm going to show you some things having to do with magnetic fields in the environment of planets and comets. The first hint that there was a magnetic cocoon around Earth, that Earth's field actually extended into space and somehow guided charged particles, came in trying to understand a strange phenomenon that had been observed during World War I, when they first used radios on the battlefield. And they would sometimes hear the radios making sounds. Now let's hope that, oh, come on.
You can turn off the pointer.
Pardon me?
If you can turn off the pointer.
Turn off the pointer.
Yeah, the PowerPoint.
Okay, thank you. Let's hope. So if you're on the battlefield, and you hear that, you think that they're bombs there. So it's very mysterious and very unpleasant. The explanation of what was going on dates to 1953, when it was recognized that Earth's magnetic field actually carries charged particles and traps them so that they go from one hemisphere to the other along magnetic field lines. This kind of sound is described as a whistler, and it develops when lightning generates a lot of electrical signals in one hemisphere, and it excites a wave that moves along the magnetic field to the other hemisphere. And this particular kind of wave has the property that the highest frequency components travel fastest. So you first hear the higher frequency, and then you hear the lower frequency. So that makes it sound like a whistle. I'm going to go back now that I know that I can operate and show you this movie, because it is great. So you can see these arches on the solar surface, and the time is going very fast. It's listed down here. But it keeps blowing up these shapes and spewing out plasma into the region around the sun, and then it travels through the solar system. So close to the Earth, the magnetic field resembles that of a bar magnet. So bar magnet, the magnetic field has this kind of shape, and that's how a compass works. If you put a compass on the surface of the Earth, you can see all the little arrows are pointing up toward the North Pole, and that's how we find the direction north when we're looking at at the Earth, which has a field that looks not terribly much different from a bar magnet at the surface. Well, that's good if you're very near the surface, but when you start moving away from the surface, you begin to find other things, and satellite exploration started at fairly low altitude and found that there were charged particles trapped in Earth's curved field in space. And I keep forgetting to use this thing. So close to Earth, we have the Van Allen belts, and here you can see that they're trapped in a shape that looks very much like this bar magnetic field, that those are energetic particles that Van Allen discovered on a spacecraft that was orbiting at very low altitude above the surface of the Earth. And every time that he was looking for cosmic rays, which had been seen on the surface before, very energetic particles from outer space. And he didn't see many as he was going around until he got to a fairly high latitude. And then suddenly, the detector measured nothing at all. And that was because the number of particles hitting they were coming so fast that it knocked out the detection mechanism. So that's how the Van Allen belt was found. So we've known since the earliest days of space exploration that charged particles are trapped in the magnetic field near Earth. More recently, we recognized that these charged particles change their properties in time, and we are learning how the solar wind, which I will get back to, controls what happens to those charged particles. It's a set of phenomena that we refer to as space weather. They're explosive changes that take place in the immediate environment of Earth that drive strong electrical currents through the ionosphere. The ionosphere is the high-level atmosphere that is itself ionized and can carry electrical current. And our department and other university faculty are leaders in studying these processes that make explosive changes in the environment. The currents that are driven by these changes that start in outer space cause very serious problems for a wired society. NOAA, the National Oceanic and Atmospheric Administration, has a space weather prediction center for making forecasts and monitoring what's going on in space. And it has listed some of the impacts, which I've separated into ones that are immediate and ones that are long range. The immediate ones, electric power transmission, the currents that flow in the upper atmosphere can become so strong that they produce results in transformers on the ground and knock out transformers. The entire province of Quebec was without power for several days once when one of these solar storms knocked out the power knocked out a transformer. GPS systems can go amiss, and if you're landing a plane, a mistake of 10 meters can make a very big difference in whether you get your passengers onto the ground or not. A high-frequency radio communication, satellite communications, and satellite drag. When these events occur, the satellites lose momentum and slow down, and then when they slow down, they can actually begin to drop out of orbit and actually be lost. So that's a serious problem. And then there are possible long-term climatic effects that are still, climate takes place over decades, centuries. So answering the question of whether solar events affect climate is going to take us a much longer time than finding out if it affects our ability to use our cell phones. Okay, so in order to understand the properties of near-Earth space, we have to return to the corona, which is the source of the plasma that surrounds all of the bodies of the solar system. Now here, the sun is eclipsed here, not naturally by the presence of the moon, but by an occulting disk, which is 3.5 times the radius of the sun. So the sun is just a small bit in the center, but in order to make good images, they have to block out a lot of the light. And so this is another video, and now they work. So well, I'll just have to oh no, it's going. It's supposed to be looping. And so you can see it's, again, very speeded up. If you want to keep track of the time, I don't think you really can see fast enough to see. Time has been sped up, but the sun is constantly sending out gases fairly non-uniformly, but almost radially from the sun, going at very, very high speed, several million miles an hour, and filling the solar system with charged particles that are moving outward. This is not directly relevant to my talk, but this particular video clip has a fun element. There is a comet coming in from the side. Remember, it's looping, so it'll keep coming in. There, you see it? It comes in from the side, and it never comes out. It burned up before it was able to emerge from the other side of the sun. I just love that. Okay, so let's go on. What happens to a comet when it encounters the solar wind? Well, the comet develops two tails. One is made of neutral dust, not charged. The sun you should think of as down at the bottom here. And the dust follows the the comet in its orbit. It's moving in this direction. So it's not quite aligned with its orbit. The sunlight actually pushes out the neutral material a little bit from the direction of the comet orbit. But there's this second tail, second comet tail, and that is going right in the radial direction toward the sun. So that's composed of ionized material that's been picked up by the solar wind. It's trapped on the solar wind magnetic field, and it is moving outward, radially outward away from the sun. So this is the direction of the ion. That's the ion tail, and that's the direction toward the sun. It's like the solar corona. It's a magnetic structure visible because relatively high density plasma is painting the magnetic field. Well, something different happens if the body in the solar wind has its own magnetic field. And here is an image of a cartoon of what the magnetic environment of Earth looks like. We can't see this because, as I've been pointing out, magnetic fields are not visible, but spacecraft exploration has shown us that near Earth, the field remains similar to that of a bar magnet. We call it dipolar. But when you get away from the Earth, first place if you head toward the sun, the region in which Earth's magnetic field is present is confined within a boundary which we call the magnetopause. We call this cavity in the solar wind the magnetosphere, and the solar wind is prevented from going closer to Earth by the Earth's magnetic field. So the solar wind is a charged particle gas. It's stuck to the magnetic field of the solar wind and has a really hard time jumping from the magnetic field of the solar wind to the magnetic field of Earth. That makes a boundary between the two. It actually is moving so fast it has to go through a shock before it can diverge around the Earth. We've used, this image uses color to distinguish solar wind field lines, which are grayish white, Earth field lines, which are red and start at one end of Earth, end on the other end on Earth. And then these few field lines that start in the solar wind and end up in the polar regions of the Earth. We call those open field lines because they're directly connected to the solar wind. And that tells us that the region around the poles, magnetically and in terms of charged particles, are going to have some very special properties. So I think I've said all this. Oh, I failed to say, this structure is very, very big. The distance between the Earth and the boundary in the direction toward the sun is about 10 Earth radii, and an Earth radius is about 4,000 miles or 6,400 kilometers. So this is a very, very big structure. The sun, of course, is much bigger. The sun's radius would be about 100 times Earth's radius. And I've told you about this. Okay, so the part near the poles is very special, and we all know about northern lights, the aurora. There are also southern lights around near the southern pole. And the aurora often aligns with the extensions of Earth's magnetic field, so you can almost, I think, believe that these are magnetic field lines that are along which the particles are concentrated. The aurora is not stationary, and here is another time-lapse video where you go through a night and you can see in some northern clime how different the aurora appears at different times, both in shape and color, intensity, It's a very dynamic process. And of course, that's been a big mystery for people from earliest times because they didn't know what was causing the fire in the sky. Well, it stands to reason that Scandinavians would have been the earliest to think about doing experiments, and one of my favorite scientists is a man named Christian Birkeland, who spent the winter of 1899 to 1900 observing aurora with some young students from a mountaintop in Norway. That sounds like this 1900. Transportation was dreadful. The weather was awful. But what they did was to triangulate from mountaintops and were able to show that the aurora occurred about 100 kilometers above the surface of the Earth. And that was really, nobody really even knew where the aurora was before that. He went back and decided he really needed to do some experiments. So he set up a laboratory and he developed what he called Torella Experiments, Torella meaning a little Earth. He had a magnetized sphere, and he put it into a stream of electrons and asked what happens. And what he found was that the electrons tended to come in a kind of crown-shaped space around the pole, just in the latitudes where we see the aurora on Earth. So he showed how a source of charged particles flowing toward the Earth into the magnetized environment of Earth would be diverted by the magnetic field, but it could move, as I've told you, particles can move along the magnetic field, and near the poles it could move along the magnetic field and excite the atoms and molecules of the upper atmosphere. And that was a very major advance in our understanding. It's actually a little more complicated. The path from Birkeland to our current understanding of near-Earth space made it clear that the magnetic field of Earth forms a barrier to the solar wind. It wasn't quite clear how the magnetic fields got linked together. It's a process we call reconnection. And people are still fighting over the details, but I think every year brings us closer and closer to a full understanding. But the important thing is there are a very small fraction of the magnetic field lines of the solar wind that hit the Earth that actually connect and form this polar region. And let's go on. So I have another great cartoon. The details are not exactly right, but it is a very good way of understanding what happens. It starts at the surface of the sun, and we've been looking at that. And what you'll see is a big arch coming out, carrying a lot of plasma from the sun out into interplanetary space, hits Earth, modifies the magnetic field configuration, causes an explosion that sends charged particles down into the auroral regions of the Earth. I'm going to show it to you again because it's an awful lot to take in one round. So the coronal region suddenly sends out something we call a coronal mass ejection. It hits Earth, modifies the field configuration in the front, causes an explosion in the back, sends particles into the upper atmosphere, and causes the aurora to brighten. And we have spent, there are people in this room who spent their entire careers helping us understand these complicated matters. But I'm going to go on from Earth to other planets because it's always interesting. If you're a lab scientist, you like to change the temperature or the pressure or different parameters and make your measurements to find out how things change when you change some parameter. We can't do that at Earth, but what we can do is go to other planets and see what happens there. And so these are the planets that have magnetic fields. Mercury. These images show you both the axis around which the planet spins and the polar region of the magnetic field, the direction of the North Pole. And you may know that at Earth, the North Pole around which the planet spins is slightly displaced from the North Pole that is identified by a magnet. That's true at Jupiter, at Uranus, and at Neptune. But Saturn and Mercury have their magnetic fields aligned with their spin axes. And I'll tell you that people are still scratching their heads over that because we don't really understand that. The other thing is, somebody asked me if I was going to talk about Mars. Well, you notice Mars is missing here. It should be between Earth and Jupiter. It doesn't have a planetary field, and Venus doesn't have a planetary field. So we have, most of the planets have planetary magnetic fields. There are great differences in various features that are going to be important in understanding magnetic structures around the planets. The solar wind gets weaker its density goes down as we move out from the sun. So it blasts Mercury, and it doesn't do an awful lot at Neptune. The other things that change, the Jupiter and Saturn are really very, very large, and they spin faster than Earth. The day is about 10 hours long. So if you think of taking a slingshot and putting a very long rope, you'll see that it really can make the spin go very, very fast. So rotational effects are very important to Jupiter and Saturn. So we have this whole range of laboratories, and we have been sending spacecraft to explore with magnetometers, measuring magnetic field, and charged particle detectors to measure the particles in the regions around these planets. So they're big and they're rapidly rotating. Each one is different. I'm going to talk a little bit about Saturn. You notice I'm showing you an image that shows that, like Earth, Saturn has an aurora, and a lot of the phenomena are very similar. So one of the things that's really interesting at Saturn, I pointed out its magnetic field is aligned with its spin axis. So you wouldn't think that anything that had to do with magnetism would be affected by its rotation. But what we've discovered is that the Saturn emits radio waves whose intensity varies at what we think is the rotation period of Saturn. Now, we don't really know the rotation period of Saturn. Why is that? Because all we see are clouds, and you know that clouds move relative to the surface of the Earth. Not very fast, but they move. And so if all you can see is the clouds, you don't really know what the inside is, what the inside period is. So at first, when we started seeing roughly 10-hour period waves being, radio signals being emitted from Saturn, everybody thought that must be the rate at which it's rotating. But big bodies don't change their rotation rate very quickly. And what we found was that these periods were changing by about 1% a year. So it had to be something not in the deep interior, but something maybe having to do with the atmosphere. And so we started looking at the possibility that there was a source of magnetic variation that started in the upper atmosphere. And working with a former UCLA PhD, we came across we were able to model what a rotating atmospheric current system could do to the whole magnetosphere of Saturn. So what you see here is a cut through the sun off to the left and a cut through the middle. The polar region where the aurora is here and down here. And what you're going to see is the solar wind isn't allowed to change at all, but the atmosphere has a rotating source of currents that makes the whole magnetosphere dance. The magnetopause, the boundary, moves in and out every 10 hours. The region of, this is, color represents density, and the high density region bobs up and down at this 10-hour period. So something is going on. It seems to give really quite good correspondence with the measurements that were made. We still don't know what makes the upper atmosphere behave the way we think it does, but we're working on that. So we have lots to think about. I'm going to go quickly now into showing you a little bit about Europa. These are the Galilean moons of Jupiter, named after Galileo, who discovered them in his telescope. Io is the one with lots of volcanoes. Europa and Ganymede, the biggest moon in the solar system, and Callisto. And using gravitational measurements, we've been able to figure out something about the interior structure. Three of them have iron central regions that we call cores. They're surrounded by a rocky layer, and that's present in each one of these. Callisto is a little odd. I won't go into that. Europa and Ganymede both have icy outer surfaces. At Europa, it's only about 100 kilometers thick, and at Ganymede, it's about 800 kilometers thick. But we did find that Ganymede had its own magnetic field, but I think I don't want to take time to go through that. I am going to jump on to Europa. We studied the magnetic fields near Europa, and we found that their shape was a little different from what we expected from Jupiter, just in the way that we would expect if there was part of the icy outer crust was melted and was an ocean. Ice does not carry electrical currents, so it can't modify the magnetic field substantially. So we needed something that could carry the electrical currents, and a global ocean would do just fine. So here is the current thinking on what the near surface part of Europa looks like, that it has an icy layer on the top, an ocean beneath the surface, and then the rocky part in the center. And we were lucky enough to be able to go back and look for a time when the magnetic signal would have a particular form if we reached it at a particular phase of Jupiter's rotation. It all worked. Well, we reported what we had seen, and immediately everybody said, oceans, water, life. And I have to tell you, there was a lot of pressure. Aha, Europa has an ocean, have you found the whales? Well, we haven't found the whales, but we have a pretty good idea that Europa is going to be a very interesting place to go. And as was mentioned earlier, there's a major mission going to Europa, and everybody's very excited about learning more about the conditions on the surface, near the surface, and whether they really can be a possible place for finding life. So we continue to explore our plasma and magnetic environment, and I'm showing you most of the spacecraft that are operational at the moment, and want you to know that UCLA has contributed to about half of them, scientific satellites that we are using to explore on the left the region around Earth, and on the right, other parts, other bodies, asteroids, comets, the other planets. We also know that the whole solar system is embedded in this outflowing solar wind, and that has to stop someplace because there is plasma and magnetic field in the local interstellar medium, in the part of the solar, in the part of our galaxy that is not in the solar system. And so we have 2 spacecraft on their way out looking for the edge of the sun's magnetosphere, which we call the heliosphere. And this is a cartoon from a couple of years ago because the journey out started in 1977. And all the way along, we've been asking, are we there yet? Are we there yet? Are we there yet? Are we there yet? And it turns out in the last couple of years, there's pretty good evidence that one of the 2 spacecraft has reached the local interstellar medium. The other hasn't quite. Their power is going down year by year, and we're hoping that they will retain enough power to be able to keep sending signals to let us know what's out there in the interstellar medium. The last thing I want to talk about is magnetosphere-like structures that exist not only beyond the solar system, but outside of our galaxy. This is a pulsar moving through the space of the intergalactic space, and boundaries observed here look a lot like the boundaries we see near Earth and the other planets. The outflow is a supersonic wind, so it's a great deal like the environment of Earth. The whole system is moving to the left and causing a bow shock to form. So I want to end, I started with the solar corona. I want to end with the solar corona. I want to remind you that, the solar eclipse. Another total eclipse will be visible from the US in 7 years. It'll go north-south this time, south-north, starting from Texas and ending in Maine. 2024, get out your calendars. When you see it, either directly or on your TV, I hope you'll think of the influence of the coronal plasma on our home in the solar system. And I want to show you, one more video, this one taken by Jean-Luc during our expedition. The eclipse is just starting, the totality is just upon us. You're going to see it getting darker. The sun is moving toward us from the west to east. You can see it getting much darker. We are going back and forth, looking first at the darkening horizon and then turning around to look at what the little bit of left of the sun with glasses off, glasses on. Now it finally gets total and everybody is so excited, pointing up in the air. It's just incredibly exciting. And then finally the sun begins to come back out. We put our glasses back on, and my granddaughter is absolutely dissolved in tears. She's so moved by the whole process. Thank you, Jean-Luc. That's such a wonderful video. And thank you, audience and time for questions.
Thank you so much. So I would like to ask our panelists to please join us at the front. We will have some assistants collecting questions, and we'll get started with the Q&A in a minute. So, Margaret, could you come?
Oh, we're going to sit down for this.
Yes. Actually, can you sit here?
Am I supposed to sit here?
Over here. Can you go all the way at the end? Sorry. All right, can you hear us? So I'll start off with a few questions while our volunteers collect the questions. So Margie, please tell us how it all got started for you. How did you get into science?
How did I get into science? Am I using this one?
Yes, go ahead.
Sort of adiabatically. I mean, in other words, it happened very slowly. I liked the science courses I took in high school. I loved doing math problems. I got to college and I found that I didn't really like math for its own sake. I liked it better when I was doing something with it. So I started majoring in physics and I liked that. So that's how I got into it.
All right.
That was not space physics, but it was physics.
Next to you is Jessica Ardinger. You are an undergraduate at UCLA, and you decided to work on the ELFIN project, which is the CubeSat that some of you may have seen outside. Oh, there it is. So you're working with this with Professor Vassilis Angelopoulos in our department. So what initially drew you to this particular project?
So I actually had no idea that UCLA was developing a satellite until one day I was at a department meeting and one of my friends, Emmons, came up to me and she's like, "You're smart. Want to build a satellite with me?" And I'm like, "Of course." So I went home. She told me a little bit about it. I went home, studied it up on it myself, filled out an application, turned it in, ended up getting hired, and now I'm the lead of the fabrication team. So I build space parts, which is awesome.
Thank you. And your team is about 40 undergraduate students, is that about right?
Yes, and there's only a couple grad students. We're mostly undergrad. And in my subsystem, I have about 4, mostly engineers. But I'm an astrophysics major.
All right. Next to you is Michaela Villarreal. You're a graduate student in our department, and you're studying space physics. Presumably you had a choice of graduate schools to choose from, so why did you decide to come to UCLA?
Yes, so I knew I always wanted to do space missions. So after doing a lot of research, looking at a lot of different schools, I found out that UCLA was a prime place to be, especially our department. We have a particular connection with JPL, and so we do a lot of joint mission work. So I decided to come here, and I was lucky enough to be part of the Dawn mission. So that's a mission that's gone to 2 different objects in the asteroid belt. It's gone to Vesta and Ceres, both in orbit. So I've been lucky enough to be part of that science team, and so I'm hoping that my experience here will prep me for future missions and that I can continue on with that journey.
All right. And then to your right is Christine Gabriels. You obtained a PhD in our department in 2014, and you're now a researcher. And I wanted to ask, how is your life different as a researcher as opposed to a graduate student?
Sure. It's a really interesting question because actually there's a lot of similarities, first of all. I actually like to use the analogy that grad school is like an apprenticeship, because in grad school you're doing the real work, you're doing real research, you're going to meetings, you're going to seminars, you're writing papers, but you have more direct guidance from the expert, the mentor, the advisor. But then once you graduate, then you do all those things, but with more on your own initiative, you have built up that toolbox of capabilities. And I think one of the more positive differences is actually the confidence that you get having proven yourself as a student and then coming out and feeling not only your own confidence, but that of the community who start treating you as more of a peer. And you kind of, I guess, build yourself to that expectation. So it's been really fun actually getting involved in leadership positions and giving back to the community that helped me get started.
All right, thank you. So, Margaret, you're surrounded by these young women in science and on this panel, and I wanted to ask, what, if anything, has changed since the time you were in their position to today?
Yeah, well, I must say it makes me very happy to be surrounded by these wonderful young women. In my classes, I was usually In my freshman year, the ratio was 40 to 1. In my graduate career, my classroom was 60 to 1. It really didn't bother me at the time, except they were all so tall and they all sat in the front row. And the other problem was that I remembered that there were lots of men in the class and couldn't distinguish one from the other, but they all knew me. And years later, people have come up to me and said, I took a class with you. And I said, some of them even remember my grades.
Jess, so you're taking a lot of classes, presumably, to complete your degree. So why did you decide to spend time on a research project? Why was that important?
So my friends that are around me have a joke that when they don't know where to find me, they go to the basement of the geology building, because it's usually where I am. And I hate to admit, or I guess I don't hate to admit, but I probably spend more time machining for Elfin than I do any one of my classes. But I don't look at it as necessarily taking time away from my studies, because Elfin's kind of like, it integrates other aspects of life and skills that will be important in the future, such as whether we have a really complicated part and we all need to get together and figure out how can we make this, especially within our tolerance levels. So for instance, every part that we machine, every feature, every hole has to be within 0.02 of an inch accuracy. And to kind of give you perspective, a sheet of paper is only 0.03 of an inch. So everything we produce, when we measure it and check it afterwards, it has to be within 2/3 of a sheet of paper. So at least in my own life, talking to some of my adult friends that are machinists by trade, when I show them pictures of the parts that we're making, they're not only impressed with just how complicated they are, but also within the tolerances we have to make them. So I'm leaving UCLA as not only an astrophysicist, but also a machinist with probably more skills than most of our engineers that leave the department.
All right, so Nikki, completing a PhD is a hard, long endeavor, and I wanted to ask about sources of support that you're getting from either fellow students or faculty or others.
Yeah, so one of the nice things about our department it is on the smaller side. And so what that means is that everyone basically knows everyone, and you build friendships, and everyone wants you to do well. So particularly the graduate students have a really good community amongst themselves. If someone's going to be doing an oral exam, the students will congregate together and try to give you a mock trial, essentially, of your talk. And so it's not always fun. They ask you questions that you're not expecting, and it's hard because you're like, oh, I didn't even think of that. What if they ask me that question on the exam? But it's also good because when you do get asked that question on your oral exam, then you know how to answer it. So we do practice talks. If we have a proposal coming up or a paper that we're trying to get out, we send it around, try to get peer communication, peer edits. Whenever we have conferences coming up, we get together and we do a special seminar, and everyone gives a 5 to 10 minute talk on what they're going to be presenting at that upcoming conference, and we give each other feedback. Maybe you can change this slide in a particular way, you can explain this better. And we just try to build each other up and build each other's confidence, because that's really hard, especially in grad school, when you feel like, as Christine said, you're trying to prove yourself. So try to get together in that way.
All right, thank you. So Christine, you do your research, your busy research work there, and then you also volunteer to do all other things. So you've volunteered to teach one of our summer courses, EPSS 7, Perils of Space, which is Introduction to Space Weather, and presumably you'll cover some of the similar topics. And then you've also volunteered to give talks at our Exploring Your Universe event, which is an annual science festival here at UCLA. So I wanted to ask, why is the teaching and the outreach appealing to you in addition to the research?
I think it boils down to the human element. I think that human nature is such that we desire community and want to know that our work is meaningful and purposeful in that context. And of course, doing science, it feels like, of course, we're doing really great things for humankind. But sometimes when you're working at your computer and you're writing computer code, it starts to feel a little abstract. So I really like to go talk to people, talk to students, because I think it helps kind of recenter and remind me, like, what's the purpose of this all anyways? Bringing it back to the people that we're hopefully helping. Yeah.
All right. I have a question for you. What advice would you give to young people who are contemplating a career in science?
Well, it's a wonderful field, and I think that the important thing is to be a little bit flexible in what you think you're going to end up doing. At least that's the lesson of my career, because I certainly didn't know I was going to be doing space physics when I started on my graduate work. My first job had nothing to do with space physics, but there are wonderful opportunities that you don't even dream of, and just be aware of the opportunities that will open up for you, and be prepared to take a jump and do something you didn't think you could do.
All right.
That's great advice. Jess, so
You're working on ELFIN, and it will measure the behavior of electrons in space.
can you explain how that is connected to the Earth's magnetic field? And
Will you learn about the Earth's magnetic field from those measurements?
So lucky for me, Professor Kivelson pretty much gave you the rundown of what's actually happening around Earth. So what we will be doing is we will be in a circumpolar orbit about 450 meters, I believe, above the Earth, or kilometers rather, sorry, above the Earth. That was the number I just learned today working at the table outside. Hopefully you guys got a chance to come and check out our project and see all the different parts. But so we will be going around the Earth, and we will actually have two ELFINs, so we're building two satellites right now, and they will go over a certain spot in the Earth, around the Earth. One will go and traverse over a point, and then only minutes later, the second satellite will traverse over that same point, and basically we will be determining the flux of the particles coming in as the solar wind, as it's coming off of the sun, it's moving at the supersonic speeds, which can push some of the particles in the magnetic field into the atmosphere. And so we're trying to determine these particle precipitations that are happening around the Earth. So hopefully we will have a better understanding and model of our magnetic field.
All right.
Sorry, very wordy.
Now, Miki, your research is about the dwarf planet Ceres, and it's occasionally observed to have a temporary tenuous atmosphere. How could that be related to magnetic fields?
Yeah, so we think that the atmosphere of Ceres is actually connected to the magnetic activity of the sun. Margaret showed that wonderful movie of the coronal mass ejection where you saw these really energetic particles coming to the sun, and it was encountering Earth, and you saw the aurora. Well, that movie was for Earth, which has a magnetic field. Ceres is a dwarf planet and doesn't have a magnetic field. So when these really solar energetic particles are coming off from the sun, they're just directly hitting the planet's surface. So what we think is happening is because these particles are so energetic, they have enough energy to break off the water bonds. And when that happens, it pops off water from the surface, and that can create an atmosphere. So what we're currently looking into is whether these solar events are indeed causing this atmosphere at Ceres.
All right. Thank you. And then, Christine, you're doing research that's connected to the phenomenon of auroras that Margie talks about. Can you explain the connection with the Earth's magnetic field there?
Sure. Well, we all saw a beautiful movie that Margie just showed in her talk that showed a lot of the science. But I thought I could maybe also give you an analogy that can help if you have your kids or grandkids asking you about it. And that's, I think most people have seen Star Wars or Star Trek, and you know that there's this invisible force shield that that spacecraft have. So I kind of have the analogy that the Earth has this invisible force shield that's protecting it from the sun as it's shooting all of this energy at us. And then sometimes those energetic particles can seep into the force shield. But then we have our second line of defense. So essentially, that force shield, that magnetic field, will stream those particles and funnel them into the northern and southern hemispheres into the upper atmosphere. And that's our second line of defense, actually, is that atmosphere. Because when these particles come in, they're so energetic, but then they ram into the particles in the atmosphere, and that takes away their energy by transforming it into light. So we have different atoms, different molecules that make up the atmosphere. And oxygen, when it gets hit by one of these particles, emits a red glow. And nitrogen, which is at a lower altitude, when it gets hit, emits a green glow. So that's why you see red aurora high in the sky and the very dynamic green aurora lower in the atmosphere.
All right. Now, I wanted to ask all three of you very briefly what the impact of a role model like Professor Kivelson has had on your development.
For me, I don't know if you all watched the recent SpaceX launch, but when they showed videos of the team cheering for joy, if you look around, you see men, a sea of men. So seeing a female be able to make such an impact and study space physics, I think that that's great and very influential in my own life.
Thank you.
Well, for me, Margie's work on Europa's ocean is particularly influential to me. When I first learned that there was another body in the solar system with another ocean, I thought that was the neatest thing ever. Margie's searching for whales. I was hoping for mermaids at the time, but maybe jellyfish too. But I just thought that was the coolest thing, and it's something to this day that I'm still passionate about. She also mentioned earlier that the Europa Clipper mission should be launching fairly soon and should get there, I think, by 2024. And so I'm hoping once I leave here at UCLA to be a part of that mission and build on the Margie's work that she originally started.
Great.
Yeah.
Well, for me, Margie is just an inspiration and an encouragement for me. When I decided I wanted to study outer space, it was because I had this idealistic impression that, okay, I want to dedicate my life to something that will really further humankind and make us better than we were before. And I think, Margie, you're just the exemplary of this type of person who has dedicated your life to the study of outer space and has improved us as a race, and it's extremely inspirational. And to have done that as a woman and a wife and a mother is a further encouragement to me to know that you can be an amazing scientist and also an amazing family person. So thank you.
All right, we have some very interesting audience questions here. Why does the sun's magnetic field reverse every 11 years?
Why doesn't somebody else answer?
All right, that's fair game. Anybody who wants to take it.
No, I'll give you that. We don't have a full understanding of how planetary magnetic fields are and the sun's magnetic field are created. But we do know that it has to do with motions, chaotic motions of conducting fluids. In the Earth, that conducting fluid is in the core. In the deep interior that is made of iron. In the sun, it's closer to the surface, but there is also a conducting layer that is sort of boiling all the time. You saw those images that really make it clear that it's boiling all the time. It turns out that these very complex motions can lead to an overall magnetic field, and that magnetic field can last for a long time in one orientation and then flip. And at Earth, there have been flips of the direction of the North Pole. At Earth, they're irregularly spaced in time. In the sun, they seem to be fairly regular. We don't really have a full understanding of that yet. But I'm sure that with the kind of work that's going on now, probably we'll get there in the next decade or so.
Maybe one of these three can figure it out.
That's right.
All right.
We have to leave something for them.
Another question, do aurora lights always occur at North Pole and South Pole simultaneously?
Well, I'll let Christine take that one.
Sure. The answer would be generally yes, but there are asymmetries, which means that, well, actually, I should explain maybe the point of the question. So the reason why you would see them both in the north and the south is if my fist is the Earth, you have the magnetic field line that's going from one pole to the other like this. So when those particles that we saw were funneling, they're going to funnel both into the north and to the south. So you can almost see a mirror of the aurora. But again, like I was saying, this isn't completely the case, and there are some people who are dedicating their research to discovering why we do see asymmetries, why they don't exactly match each other.
All right. And then the question says here, if Mars doesn't have a planetary magnetic field, what protects us from solar rays? And maybe that's true at Ceres as well.
Yeah, I can take that one. Yeah, so Mars doesn't have a magnetic field or a dynamo, but it does have an atmosphere. And what happens is the solar radiation coming in can ionize the particles in the upper layer of the atmosphere. And what happens is you get a current that's induced on the surface of the ionosphere, and that actually shields Mars from the solar wind. So you saw in those graphs that Earth had that nice bow shock in the front that protects it from the solar wind. So you get the same phenomenon at Mars, except it's much, much closer to the planet. It's not very far in terms of distance like it would be for Earth. But you do get protection even without a dynamo if you have a strong atmosphere.
All right. Next question is there a tilt to the solar axis relative to the ecliptic, which is the plane about which the planets rotate? And what effect, if any, does that tilt have on the solar wind or solar weather?
That's a good question. Shall I take it?
Sure.
Okay. The sun's rotation axis is tilted by 7 degrees relative to the plane of Earth's orbit. And it has an effect in the sense that the magnetic field of the solar wind has a preponderance of orientation relative to the Earth's magnetic field that varies seasonally because of the tilt of the sun's axis, because we're always moving around. So for part of the Earth is moving around the sun, and so sometimes the tilt is toward the Earth, sometimes the tilt is away from the Earth. And that tilt does change the structure of the magnetic field that's incident on the Earth and produces a seasonal effect in the amount of what we call activity, things like aurora, how intense the aurora is, how significant some of the other dynamical processes that I talked about, like sending radiation into the upper atmosphere and affecting GPS. There is a seasonal variation that relates to the tilt of the sun's spin axis.
The next question is, if the aurora mostly follows the magnetic field lines, does that mean, and the aurora is very variable, does that mean the magnetic field is moving or not steady?
You want to do that?
Yeah, actually, when you look at, if you can try to remember what Margie's movie was like, you could see that when the solar wind hit the Earth's magnetic field, that caused a lot of the tail, so the part of the magnetic field that is behind the Earth compared to the sun, to move a lot and to what Margie called reconnect. So these field lines reconnect. And then when they do that, they spring towards the Earth in that explosive manner, which then sends those particles streaming into the atmosphere. So yes, the magnetic fields are extremely dynamic, especially during these explosive events.
All right. A more technical question here. What causes whistlers to have higher and lower frequencies or to move at different speeds?
Well, that's a hard question. I could say that's what the equations tell us. Why do they tell us that? Well, it has to do. I don't know that I'm going to be able to.
Maybe we can just
think of
focus
a great
on.
way to answer that question that doesn't just use equations.
But wave propagation in a plasma is complicated, and different frequencies do get affected differently, right?
Let's just take an analogy. I think that's an easier way of dealing with it. You know, the different colors of the visible spectrum have different wavelengths and different frequencies. And as you pass a white light through a prism, the different frequencies spread out because of the way they interact with the material of the prism. And it turns out that the blues bend more than the reds because they interact slightly differently with the material of the prism. And so I would think this is something of an analogy. The whistler is an electromagnetic wave, so is light. It's moving through a medium of electrons, and the relationship to the electron motion differs slightly depending on the frequency of the wave. And so some can move faster and some move slower.
That's a great answer, without the equations. All right, there's more fairly technical questions here, and if you ask one of these, I would encourage you to come and ask directly with our panelists. But I'll end with this question. Why wasn't it completely dark during the eclipse?
Anybody else? Okay, why wasn't it completely dark? You know, I wondered about that. I mean, I think it's partly that during part of the eclipse, there is the finite size of the sun itself means that some of the light, no, it isn't the finite size, it's the scattering through the atmosphere the scattering of the light that comes through means it isn't moving in exact straight lines. And so some of it gets bent a little. I think that's the dominant.
Right.
Is that what you think?
Yeah, and there's probably some diffusion from beyond the cone of the eclipse itself.
Right.
All right. If you have additional questions, I would encourage you to come and talk to our panelists. Thank you very much for coming.